Great, thanks so much, Kyle. So I'm Wendell, I'm a master's student at the Nicholas School studying energy and environment. Our teammates and I are very excited to be here today to tell you about our work for the past year. I'm going to let them introduce themselves, starting with Ben.
Yes, hi everyone, I'm Ben Alexander. I'm a junior studying statistics and computer science.
Hi, I'm Atsushi Hu, a sophomore studying mathematics and philosophy.
Hi, I'm Varun Nair. I'm a sophomore studying computer science and math.
Hi everyone, I'm Lin Zuo, and I'm a junior studying statistics and computer science.
Fantastic. So our work is focused on training deep learning models to identify electricity infrastructure and aerial imagery to help with electricity access planning. So in this first section, I'm going to give us the background of electricity access, the topic at hand really, how electricity access planning is carried out, and then how our deep learning methods can really fit into a larger pipeline. So first, electricity access is really the backdrop to this whole project. About 1 billion people worldwide lack access to electricity, which has major implications for their well-being, social, economic development. And just to kind of hit home these points a bit, we'll look at a few statistics. So with increasing access to electricity, maternal mortality rates decrease. Similarly, there are implications for educational attainment. With higher access to electricity, there's greater attainment. And then metrics for poverty also decrease with electricity access increases. So these are all correlations, but they hopefully give you a sense of the urgency of addressing this problem. Now I'm going to be shifting gears to talking about how electricity access planners face challenges on the ground and what those challenges include. So first off, the scale of the problem is hopefully pretty clear, about 1 billion people across 2 continents. If you look at these actual populations, they're overwhelmingly rural, which adds an additional element of the challenge. So if you look at this diagram on the right, for the country of Angola, about 60% of the population is rural, and only about 3% of that population has access to electricity, versus about 50% of the urban population has access. And this trend is true for many of the countries that's seen here. And so that really raises the question for planners, how do we extend access to these overwhelmingly rural populations spread across large swaths of land? Are grid or off-grid technologies better suited to this challenge? To help address this question, there are what's called electricity access optimization toolkits. These toolkits look at the feasibility of grid and off-grid power solutions such as microgrids using hydro, solar, wind to extend access to 100% of a study region. So in this case, a team at the World Bank looked at the country of Zambia and carried out one such study using the electricity infrastructure. You can see these dark black green lines here. They represent high voltage transmission towers and power lines, along with other geospatial data to determine the least cost pathways for every point on the map. So just to unpack this map a bit more, in the northeast you see a light yellow, which represents a recommendation for home-scale solar systems, versus you can see a very large portion of the southwest is a darker yellow, which represents community-scale solar mini-grid solutions. And along the transmission infrastructure, you see the recommendation for grid expansion. So grid expansion is clearly dependent on the availability of data on the grid infrastructure itself, which can be surprisingly difficult to obtain or non-existent for many developing countries. If we don't know where the electricity infrastructure is, we don't know if grid extension is a feasible option for these populations. Our team believes that using modern computing techniques and remote sensing data, such as aerial and satellite imagery, we can help fill this information gap and automatically identify this infrastructure. So now to give you another kind of big picture look at the goals for this project, we'll set through kind of a conceptual pipeline. So if we have high resolution imagery for an area, we have a computer model that can identify transmission and distribution towers. So in this case, these smaller blue towers blocks represent the distribution network, and these magenta ones represent the larger transmission towers. Then we can turn this data into geospatial data that can be handed off to policymakers, planners, maybe people using a similar model that I described for the country of Zambia. Our work focuses on this center step, creating and training a deep learning model to identify the infrastructure itself. So we chose deep learning because of its ability to find abstract meaning in images. So to give you a sense of this, I'm not going to get into the weeds explaining deep learning, but a conceptual understanding of how deep learning works flows as such. If we wanted to train a deep learning model to identify faces in images, first we'd need a large data set of images with faces in it to train the model so it can learn important features, which it learns starting small, so it's a hierarchical model. It starts small and then works its way up to more and more abstract components of the image that give it insight if there's a face there or not. So walking through this diagram, in the first layers of the model, the model might extract small edges, dots, and curves in the images themselves that get used in later layers of the model to determine slightly more abstract features. In this case, you can think of features of a face, eyes, nose, and mouth. But critically, we don't know and don't get to tell the model what features to find important. The model determines this by itself. Later layers then can combine these medium layer features into what really determines and allows it to accurately identify faces. And critically, it's able to identify faces of people that it's not seen in any photos whatsoever. So this is really the power of the abstraction and the capability of deep learning models. Deep learning goes beyond facial recognition. Another exciting field and application for it is self-driving cars. And this example shows a model that is able to detect a number of objects that are relevant to a safe driving car software system. So, and our tools actually, our work actually has more object detection component to it than the simple binary classification. This is something that Varun will explain more so in the next sections.
All right. So now that Wendell has given you an idea of why exactly deep learning might be a suitable approach, let's take a look at some of the approaches that we took over the course of the semester. So initially we took a binary classification approach. And in this approach, we want to know in a piece of imagery, is a piece of energy infrastructure in it or not? And so in these 4 examples here, we train a model to be able to tell us that it has a piece of infrastructure present in the left 2 images and no infrastructure present in the right 2. But this isn't enough for us to be able to generate a full-blown map of energy infrastructure. For us to be able to do that, we need to know precisely where in the image a piece of infrastructure might lie. And for that, we need object detection. And so if we take the same 4 pieces of imagery, we can actually use an object detection model, which is what we used in our project this semester, to actually draw bounding boxes around where it sees different types of infrastructure in the image. So as you see here, in the left 2 images, we've actually drawn boxes around where it sees types of energy infrastructure. And it's important to note that in this image here, we have 2 boxes because we have 2 pieces of infrastructure there. And similarly, for images where there are no boxes present, we don't want the model to draw anything there. And so this is the approach that we ended up using moving forward because that would be able to tell us precisely where an image infrastructure might lie. And you might be wondering, where are we getting all of our data from? Well, our data was compiled as a part of a prior Data Plus project, and contains imagery from all over the world. In particular, we chose to focus on these 4 locations that you see here, primarily because they represent a wide range of geographies, and because they contain the most amount of annotated examples in the data set. So to give you an idea of what exactly that data looks like, consider the following typical energy infrastructure pipeline. So energy might be generated at a power plant, it is then scaled up and then transmitted across long distances by transmission towers, and then scaled down and distributed to residential, commercial, and industrial entities through a distribution network. So on a ground level view, we're more familiar with something that looks like this. If any of you haven't seen a substation before, there's actually one right behind Gross Hall that you can go take a look at after the presentation. From an aerial view, this is what our team is more familiar with looking at. And so these are what each of these 3 types of infrastructure might look like from an aerial perspective. And this data set actually contains bounding box annotations for where the different types of infrastructure lie. So you can see those 3 types of bounding boxes drawn there. Our project in particular chose to focus on the latter 2 that you see here, primarily because they contain the most amount of examples in our data set. So we thought that if we could map out most of the transmission and distribution infrastructure, we could then be able to extrapolate where the substations lie. So with that, I'll hand it over to Atsushi, who's going to talk more about the research questions that we explored.
As my colleague Wendell and Varun have introduced what tools we are looking at and what is our data set, now it's time to zoom in a little bit more and see what are the specific research questions we were investigating. So first of all, we know deep learning works, and it works on data set that contain like common objects in daily life, such as cars, chairs, cats, and everything that you see in daily life. However, we are not 100% sure that it will work on data set, and we have no idea how well it's going to work on our data set. Therefore, our first research question is to find what is the best model to work for our data set. And the second research question is we are going to face data sets from very different geographies. Especially as we introduced before, we hope to investigate how the electricity access situation in rural areas and less developed countries. The consequence is that we will be having less data for those regions, and that means we will have less training data. So ideally, we are able to train on existing data and have a model that is able to generalize on other geographies. So we hope that our model is generalizable. Therefore, we are going to carry out experiments with data sets featuring different geographies. For example, we may train on the Arizona dataset and see how well it's going to predict on North Carolina dataset. And the next problem we may be facing is that we may not have high-resolution image for many parts of the world. And the high-resolution image will be really expensive to obtain. And here is some example of the image at different resolution looks like. So the 0.15 meter resolution image will be really expensive, while the 1.0 meter resolution image will be public available. So you want to see, as we lower the resolution of the image, how much the performance will decrease, and what is the requirement for the resolution for us to obtain a model that performs well. So next, I will be handing over to Ben to talk about the method.
All right, yeah, so now that we've seen why this topic is important, why we're working on it, and as well also seen some of the specific research questions that we're trying to answer, we want to just go a little bit through some of the specific methods that we've been using for the last few semesters to answer a lot of these questions. So first we'll start with just a high-level overview of the overall pipeline, and then we'll step through it in a little more detail. But overall, the first step we had to do was image processing. So we heard a lot about the data set a few minutes ago, but the data had to be prepared in certain ways so that it would be ready to be put into the model for training. So the first step was processing. Secondly, we were able to train the actual model using the image that we had just pre-processed. After training, we were able to evaluate the performance of our model by testing it on a test set of imagery that had not been trained on. So the model had never seen it before. And then once we have done these three steps and we have a model that we're happy with, that we've evaluated, we can start mapping out grid networks in the areas that we're actually trying to study. And then we could then provide this information to policymakers and other groups who may need it for various reasons. So this is, again, a high-level overview. But going into a little more detail on the initial image processing, as I mentioned, the data that we originally had was collected from various sources, so it wasn't in exactly the right format that's needed for training. So to give you an example, one of the main things we had to do to get it ready for training was to make the images smaller. So the original images, as you can see, are very large. They're about 10,000 by 10,000 pixels, which is actually quite a large image. So the issue with that is that when you're training deep learning models, you need to use a special piece of hardware known as a GPU, or a graphics processing unit, which is really optimized for a lot of different matrix operations that are sort of the core operation needed by deep learning models. So in order to fit these images into the GPU, they have to not exceed the GPU's memory requirements. So we had to cut these large images into these smaller patches over here on the right, which are 512 by 512 pixels. And one other thing, we did overlap the patches slightly when we were slicing up this image to try to prevent things from being cut off on the edges of the patches. So once we have prepared the data, we can begin model training. So the way that training a deep learning model works is you take your data and you feed it into the model. And by giving this data to the model, it starts to look at the images and find patterns that it associates with the types of objects that you're looking for. So for example, here we have this transmission tower right here. So in this case, by feeding in this image into the model would begin to look around the place where you told it had a transmission tower, and it would start to learn patterns in the pixels. So here maybe you would see that these types of gray lines in this particular pattern are often associated with transmission towers. Interestingly, it may also look at things like shadows. So in this case, looking at the shadow is actually maybe more useful than looking at the part that's in the box, because the shadow kind of actually looks like a transmission tower that you may have seen from a slide a few slides ago. So it may be picking up on other cues like that. Similarly, it may also learn from the background. So here, there's nothing here. So it'll actually learn not only from where there is an object, but it'll also learn that these things that look just sort of like brown is probably not a tower. This model, just as a reminder, this is the same type of stuff that Wendell was talking about that's being used for all sorts of really exciting things like self-driving cars and other types of things like that. So this is just the same types of techniques, but applied to satellite imagery and aerial imagery. So once we've trained the model, we can start to evaluate it to see how good of a job it did. So I mentioned before that we had a set of test imagery, which is a bunch of images that we set aside from the beginning, and we intentionally did not train on this imagery so that the model will have never seen it. So then when we test on it, it's sort of a fair comparison. It doesn't have any knowledge from seeing it before. It's brand new. So in this case, we've basically given this image to the model, and we've said, now that you're trained, tell us where are the towers in this image. In this case, the model has said that there are 3 towers, which are right there. So then we take those labels that come out of the model, and we map them back onto the original coordinates of the large image, so that we can move on to the next step, which is evaluating the actual performance. So on the previous slide, when we come out with this output from the model, we can of course look at it and see, in this case, it seems to have done a pretty good job. But we wanted to come up with an actual way of quantifying, a more rigorous way of quantifying how good of a job the model really did. So we designed a scoring metric for this. And the way the scoring metric works is that for each tower, we say that the tower has been correctly identified if it's within a 2.25 meter radius from the center of the true tower. So to make that clearer, so let's look at this one up here. So this white dot here in the middle of the circle is the center of the true tower, the one that you can see in the image. In this case, we would say that this has been correctly identified because this green box up here is a tower that the model has identified, and we say that because that tower is within the radius, which is the circle from the actual tower, then that one's correctly identified, or a true positive. Similarly, here we have a false negative, or a missed detection, because there's clearly a tower here, but the model has not labeled anything there. And then over here we have a false positive, which means that the model said that there's a tower there, but there definitely is not a tower there. So once we've decided whether each tower was identified or missed, we can calculate the precision and recall, which are metrics that are commonly used for this type of task. So the precision is the number of correctly predicted towers over the number of predicted towers, and then the recall is the number of correctly predicted towers over the number of actual towers. So to make that a little more intuitive, the precision is basically telling us of the things that the model said is a tower, how many of them really are a tower. And then the recall is saying, of the actual towers there, how many of those did the model find? So you can see they're both very important things. They're slightly different, but the main thing to keep in mind is that you want both your precision and your recall to be as large as possible, which means as close to 1 as possible. So to show an example of a PR curve, this is a precision recall curve, which is a way of visualizing precision and recall. The ideal performance, or over here, the perfect performance, would be, as I mentioned before, having a really high precision and a high recall, which in this case means high in the vertical direction and far to the right. So that would be perfect performance over there, but that's probably would never really happen in reality. Some more realistic curves look like this blue line and this red line. And again, as I mentioned, being farther to the top right is better. So in this case, the blue line would be considered to be better than the red line in terms of performance. So we're going to be seeing a bunch of these PR curves later, especially when we're examining the results of our experiments. So just when you see those, the main thing to keep in mind is that the lines that are farther to the top right are the better ones. All right, so lastly, once we have the model that we've trained and that we're pretty happy with its performance, we can start using it to identify grid networks. So this involves taking data, imagery from the location that we're trying to study, and feeding it through the model, having it tell us where the towers are. And then we can take those labels that it outputs and convert them into geospatial data, which can then be turned into things like that sort of look like Google Maps, but with towers labeled on it, and that could then be provided to policymakers in a hopefully convenient format for them. All right, so
to see the results of the model. So let's see what model performs best for our problem. So in order to figure out which is the best model for our problem, we really want to maximize use of our data. So we trained 3 models which are faster RCN, YOLO version 2, and RetinaNet. And these are the 3 models that really gives excellent performance when they are tested on more commonly seen data. So we carry out experiment on these 3 models and feed all the images we have from the 4 different locations throughout the United States. And so from the models, we carry out predictions on our test images. And here are 2 examples of how the models perform. So you can see from the image on the right, all 3 models are able to identify both of the transmission towers. However, we have some other images that will tell us, no, the 3 models are not all equally capable. For example, you see the YOLO version 2 is only able to identify 1 distribution tower from the image on the left, while fast RCN will do better and identify 2 transmission towers. However, RetinaNet is able to perform better than the other 2, even though it is still not giving a perfect performance. However, it is still too early to say that RetinaNet is the best because we want a more quantitative measure of the performance of the 3 models. So we generated a PR curve, and from the PR curve, we realized that faster RCN will be able to achieve a higher recall value, which means out of all the transmission tower and the distribution tower, it is able to find more of them. However, RetinaNet is always having a high precision. So when we are making decision to pick from RetinaNet and fast RCN, we have to go one step further to consider our future investigation, which is to map out the grid pattern. So if we see the image on the right will be familiar to you since we have seen it before. So let's investigate some hypothetical scenario of what happens if we do not have perfect precision and recall. So first, for example, let's see how the image on the right is different from what we see just now. One of the distribution tower is missing, and that happens when we don't have a perfect recall value. However, if we are trying to figure out the grid network, we are still able to connect the dot because it will have distribution towers on the left and right to it, and we are still able to draw a line. And then what happens if we do not have perfect precision? We have a distribution tower that's out of nowhere, and it is very difficult to connect it to the existing lines. But however, this will be less of the problem if we have high recall and able to draw clean lines in other places. So we'll be able to filter it out. So ideally, we want the models to give out high recall and high precision at the same time. And the problem with faster RCN is that it has slightly higher recall value than RetinaNet. However, the expense of it is the precision goes really low and it goes to as low as 0.2 when the recall is about 0.8. That means for every 1 tower that it detects correctly, it is going to give out 4 false positives. And this will be really problematic when we are trying to draw out the grid pattern. Therefore, we think that RetinaNet is the best model we have for our problem. And
So as my colleague Atsushi has mentioned, the generalizability of models are really important, so this is our second experiment. After identifying that RetinaNet is the best performing model, we went on with that architecture and trained 5 models. These 5 models are trained on Connecticut data, Kansas data, North Carolina data, Arizona data, and USA data. So when we say USA data, it is actually referring to the data from all these 4 locations that are lumped together for training purposes. So after training these 5 models, what we did was to test on images from different locations. So here's an example where we test the model performances on images from Arizona. We can see that here are 5 PR curves, which are evaluation of model performances that my colleague Ben has just talked about. We can see that USA model has the best performance, and then comes the model that is trained on Arizona, and then the model that's trained on North Carolina, and then Kansas and Connecticut. So after that, we also tested these 5 models on the other 3 locations that we have mentioned. And from these PR curves, we have found 2 really interesting findings. The first one is for models that are trained on very different geographies, they cannot perform well enough on each other. So for example, here, for a model that is trained on Connecticut, it actually performs the worst for images from Arizona. And then vice versa, for a model that is trained on Arizona images, it also performs the worst for images from Connecticut. We speculate that it is possible that most images in Arizona represent the desert, while images from Connecticut represent suburban areas. So that might cause the difference. And then another interesting finding is that the USA model performs either as well as the model that is trained on the test location, or even better sometimes. So this is an example where the USA model performs even better than the Arizona model for images from Arizona. And here is another example where USA model performs better than Kansas model, which is trained on images from Kansas. So just to give you some concrete idea of what that looks like, here are 2 example images from Arizona. And here are the prediction results from Connecticut model. We can see that in this image, Connecticut model wasn't able to detect any towers, although they're pretty obvious there. And then in this example, Connecticut model was able to detect a wrong object, which is actually a roof corner, which is not the transmission tower that we are looking for. And then this is an example where USA model performed better than, this is an image from Kansas, and the USA model appeared to perform better than the Kansas model. Here, the black boxes indicate the results from USA model, and USA model was able to capture all the towers available in the image, but the Kansas model is only able to find 2 towers among 3 of them. So yeah.
All right, and so for our 3rd and final experiment, we want to know how exactly will model performance differ at varying resolutions of the imagery that we use. So to give you an idea of what imagery looks like at different resolutions, we've taken an image from Arizona, and we've downsampled it to kind of display it in several different resolutions. So as you can see, the piece of energy infrastructure, a transmission tower, is most clearly visible in the 0.15 meter data, and then gets harder to see as you go down in resolution. So the important thing to note for each of these pictures is how exactly each of the images were captured and how easy they are to access. So for the 0.15 meter data, this type of data is only available if you capture it from an airplane. So you need to fly over very expensive equipment over a location and capture it that way. And of course, that type of imagery is very proprietary. Similarly with 0.3 and 0.5 meter data, you can access that data by accessing satellite imagery, but once again, that's proprietary data that's very expensive to obtain from a very select amount of sources. Now, when we get to 1, 3, and 10 meter data, you'll see that it's much more widely available. For example, we have 1 meter data for all of the US, and we have 10 meter data for for the entire world. However, the trade-off that comes there is that the tower itself becomes very difficult to see. So in this problem, we're trying to explore, is there a balance that we can strike between accessing imagery that's of low cost and easy to access, and can we also have that imagery give us good model performance? So we actually trained imagery from all those 6 types of resolutions and tried to see how exactly model performance varied. And as expected, the orange curve, which represents 0.15 meter data, gave us the best performance. And this is as expected because the towers are most clearly seen in that resolution. Similarly, 0.3 meter data gave us fairly good performance. However, any resolutions of 0.5 or coarser didn't give us very good results at all. In fact, you won't even see the curves from 3 and 10 meter data because they didn't actually output any results at all. So that just seemed to indicate that the model didn't learn anything about energy infrastructure. To give you an idea of some examples that the model outputted, you can see here on top examples of imagery at different resolutions. And so here we see 2 transmission towers, and the 0.15, 0.3, and 0.5 meter data all found those transmission towers, but when we get to the 1 meter data, we were only able to find 1 of the 2 towers. Similarly, for distribution towers, that cutoff happens much earlier, in fact. So in 0.5 meter data, we were able to find 3 of the total 3 distribution towers there. But when we get to 0.3 meter data, we only found 2 of the 3. And when we get to 0.5 and worse, we don't find any towers at all. So that kind of gives you an example of at what resolution we're able to find what types of infrastructure. So moving into sort of conclusions from our project, what exactly did we find? Well, in our first experiment, we explored, was this approach, this deep learning approach, even feasible? And we found that the RetinaNet model of the 3 models that we tested gave us the best performance of a precision and recall of about 0.65. Now, we think these results are pretty encouraging. There are perhaps some more hyperparameter tuning that we've done with the models, and then, of course, adding more data will improve the model performance as well. Secondly, for the experiment in which we explored the geographic generalizability of our model, we found that if you train a model with several different geographies, it's actually able to aggregate knowledge about energy infrastructure in those geographies and apply it to improve performance. So in the example that we saw here from USA and Arizona, when tested on Arizona, the USA model actually combined its knowledge of energy infrastructure in other geographies to do better than the Arizona model itself. And then finally, we explored the resolution performance and saw that the 0.15 meter and 0.3 meter data were the best resolution, or that were the only types of imagery that we were able to get good results with. Anything of 0.5 meter data and worse, we weren't able to get good results with. Now, it's important to note that these are our particular results for the particular geography that we tested, and that was Arizona, and that testing in other geographies might change this threshold a little bit. So what's next for us? Well, we're actually releasing our data on our code on GitHub. Perhaps if any of you in the room would like to play around with our data set and some of our code, you're more than happy to do so, and we hope to have that out fairly soon. The second is to sort of continue research in this space. The main challenges going forward will be how exactly do we apply these deep learning models at scale? You know, we saw earlier the example of Zambia. We don't quite know what sorts of challenges will come up when applying this sort of model to an entire country. We anticipate that some of those will be how exactly will the model generalize to different types of geographic domains, as we mentioned here, and also being able to identify different rare objects. So being able to identify every type of piece of energy infrastructure will be able to give us that full picture of what does a country's energy landscape look like. And then finally, we wanted to further collaborate with some of our partners. The lab has worked with different NGOs and development organizations, including the World Resources Institute, and we want to continue to share our data with them and some of our findings so that we can give to them a potential solution to closing the gap of over 1 billion people that still lack access to electricity. So a couple people would like to thank, a special shout out to Dr. Bradbury for his tireless effort in helping us this semester. He's been a really good mentor for all of us, and I don't think we would have gotten anywhere close as we did without him. So a special thank you to him. We'd also like to thank Dr. Leslie Collins, Dr. Mark Julin, Dr. Jordan Miloff, Dr. Robin Meeks, Artem Shalsov and Bao Hong for their help as well. And in particular, we'd also like to thank the Bass Connections and the Energy Initiative for their financial support, as without them, it wouldn't have been possible. So that concludes our talk today. We'd like to thank you for listening. If you have any questions, we'd be happy to take them, but thank you again for coming.